Some of the biggest, most powerful changes in our world happen at a level we can't even see, the molecular level. It's this silent, invisible process of things just mixing, combining, and disappearing into one another. So today, let's dive into this hidden world and really explore the chemistry of the mix.
To understand just how important this is, let's start with a huge question. We all know about these incredible, vibrant coral reefs, right? They're home to like a quarter of all marine life, but they're in big trouble. And part of that threat comes down to a really fundamental chemical process. So what on earth makes something as massive and solid as a coral reef start to just disappear? Well, the answer, and this might surprise you, comes down to the very same principle that explains how sugar vanishes into your morning coffee. It is all about the chemistry of solutions. And once you get this one concept, it unlocks everything, from the health of our oceans to how one of those instant cold packs actually works. All right, so to really get that big picture, we first need to get familiar with the key players and the rules they play by. Let's break down the basic rules of the mix. First things first, what even is a solution? See, it's not just any old mix. A true solution is what chemists call homogeneous, and what that really means is that it's perfectly, absolutely uniform. Once it's mixed, every single drop is an identical twin of the next, right down to the individual molecules. Now, inside every solution, you've got a solvent. Think of the solvent as the boss. It's the component that's there in the largest amount, and its main job is to do all the dissolving. Water is so incredibly good at this, we even call it the universal solvent. And, well, if the solvent is the boss, then the solute is the thing that gets dissolved. It's the substance that's there in a smaller amount, the one that seems to just vanish into the solvent. So let's go back to that sugar and water. The water is your solvent, right? And the sugar is the solute. The sugar doesn't actually disappear. Its individual molecules just spread out so perfectly and evenly that they're hiding among all those water molecules. So here's the bottom line. All true solutions have these things in common. They're totally uniform. The solute stays mixed in forever. You can leave it for 100 years, and gravity won't make it settle to the bottom. The components are broken way down to the molecular level, and the whole mixture usually ends up taking on the physical state, liquid, gas, whatever, of the solvent. Okay, now this is where it gets really, really interesting. This whole dissolving process, it isn't passive at all. It's actually an active, energetic tug of war happening between molecules. It's all about breaking old bonds and forming new ones. And this tug of war happens in 3 steps. First, you have to put energy in to pull the solute particles away from each other. Second, you need a little more energy to push the solvent molecules apart to make some room. And then, finally, energy is released when brand new bonds form between the solute and the solvent. This whole energy balance is everything. It's what decides if the final solution gets hot or feels cold to the touch. It all comes down to a simple question. Which side won the tug of war? Did the process release more energy than it used up, or was it the other way around? It's pretty simple, actually. If forming those new bonds in step 3 releases more energy than it took to break the old ones apart, that's an exothermic process. It gives off heat and the solution feels warm. But if it took more energy to break those old bonds than you got back from forming the new ones, well, that's an endothermic process. It has to pull in heat from its surroundings, making everything feel chilly. And believe me, this isn't just theory. This is hot and cold chemistry that you can literally hold in your hands. Let's look at a couple of really cool, real-world examples. Have you ever used one of these for a sprained ankle? An instant cold pack is just a perfect demonstration of an endothermic process. Inside, you've got a bag of water and some solid ammonium nitrate. The second you break that inner bag, the ammonium nitrate starts to dissolve. And that process is so incredibly endothermic. It's so hungry for energy from its surroundings to pull those particles apart that it can make the temperature just plummet. And bam, you've got that instant icy cold. And then you've got the total opposite. If you dissolve a chemical like sodium hydroxide, you might know it as Li, it's incredibly exothermic. The attraction between the Li ions and water molecules is so powerful that it releases a massive amount of energy. I'm talking enough heat to make the solution dangerously hot, sometimes even boiling the water right there. So we've seen how dissolving solids in liquids can create these hot and cold reactions. But the world of solutions is so much bigger than that. In fact, they exist in every single state of matter: solid, liquid, and gas. I mean, just look at this. The very air we're all breathing is a solution. It's mostly oxygen gas dissolved in nitrogen gas. That fizzy soft drink you love? It's a solution of carbon dioxide gas dissolved in water. And you can even have solid solutions. Brass is basically just solid zinc dissolved in solid copper. Wild, right? The big takeaway here is that once you know what you're looking for, you start to realize solutions are absolutely fundamental to our world. They're in the air, in the oceans, and yep, even in the metal coins jangling in our pockets. So, from the air we breathe to the oceans themselves, our world is just this dynamic, constant mix. And that brings us right back to those coral reefs. They're disappearing because of a solution playing out on a global scale. All that extra CO2 in the atmosphere dissolves into the ocean, changing its chemistry and making it harder for corals to survive. It's the chemistry of the mix, writ large. So now that you know the rules, what's the most surprising solution you'll notice in your world today?